Okay. So if I say that there is a programming construct in a programming language, I say if then else construct. Okay. And if I ask you to generate a context-free grammar representing that, okay, in order to represent that programming construct. So would you be able to do that? If I ask you, like, let me repeat my question, rephrase my question. Okay, I'm saying that there is a programming construct in most of the programming languages, and programming construct is if then else architecture. If condition, then do these statements, else do these statements. Okay, so if I say that you have to represent this construct using the context-free grammar, then do you find some difficulty in it, or do you think that yes, you will be able to do that?
So I don't know whether this is the right thing or not, but so okay, in case this question, we could say, okay, there's a if statement on the left side, like of the production, and then we start with a if. If is a terminal, right? Then we start with a expression. Uh, then after that we can go down to another body of statements, and then no, I will have difficulty. Like I have some idea. Like okay, if I can I use a whiteboard?
Okay, let me use a whiteboard. Okay. So whatever you say, let me just write it on a whiteboard. So you're saying that okay, if you will be writing, are you able to see the whiteboard? First of all, tell me.
Yes, sir.
So do you want to say, Suyash, do you want to say that if is on the left hand side of a production and then you have something on the right hand
If
side?
statement or if block,
Uh-huh.
because it will if block. So because there are multiple different types of statements, right? There could be if else if block. It could be if else block. It could only be an if block.
Okay, so
So
you're saying
it's
that,
better that.
so you're saying that if and then some condition, okay, let's say this is some condition and then you have a block.
Right.
But
So
I am
it
saying,
will be
see,
like.
okay, fine. Okay.
So what I'm saying is in the grammar rule for it, we write a if statement on the left hand side.
If statement on the left hand
Statement,
side.
right? This is a non-terminal.
But this, how can this be a non-terminal? This is a
Because
terminal, right?
yeah, this is okay. That's the thing. So okay,
We can use this to solve using the production rules.
Okay, what is a
it's
production
not.
rule? What will be the production rule? So if is a terminal, you cannot use it on the left hand
Yeah.
side. Okay, on left hand
Yeah,
side,
this is
only
the
non-terminals
right hand
comes.
side. This is for the
Okay.
right hand side.
Yeah, if should be on the right hand side.
Right. So this is if. Then there is an expression.
It is on the right hand side.
Okay. Okay. So this is for if. Then this is next expression.
Okay, let me say
So
here, it is on the right hand side.
yeah.
Okay, and
Okay.
let's delete that circle.
Okay. I
Okay.
thought it's for the left hand side.
No, this
Yeah.
one is
Okay.
the right hand side. This
This
one
is
is the left
terminal.
hand side.
It's a terminal, right?
Yeah, it is a
And
terminal. So you should write terminal here,
right.
T, capital T.
Yes, sir. Right. Capital T or
No,
just.
see, let me just clear one thing over here. So you do not need to define that this thing is a terminal, this thing is not a terminal. Okay, so you can take it for granted. Okay, you can take it for granted if it's a terminal. You don't need specific thing to say that it is a terminal. Okay,
Okay.
so what you need to do is you need to define something like S, like this is a statement. Okay,
Hmm.
statement like if, okay, and then you can
An
have
expression.
let's say expression
Expression.
or a condition, let's say condition.
Right.
Okay,
That is a
okay,
non-terminal. This is a non-terminal.
okay. If do you want it to be a non-terminal, okay, let it be a non-terminal.
Yes,
Let's
sir.
say
Because it could be any type, right?
let me write capital E for that matter. Okay, expression.
Right.
Okay,
And
and
then there could be
there could be another
What
there could
was
statement.
the
be a starting
question?
symbol here. So for the block,
No, I am asking that can we write capital S over here?
Yes,
um,
sir, it is possible.
no, sir, not in this word. Like, can we write one?
Yeah, we can
Uh,
write anything. Okay, can we write what?
okay. So my idea was okay. This if else. Okay, then they have the body of statement like a block of
So
statements.
E
So
stands for expression. If E doesn't
right,
stand for else.
E stands for expression.
Okay,
right?
let me see capital C, if condition.
Okay,
Okay, so
then
then
there has
let's say we have a then over here. Let's say we
uh,
do not have this here. We do not have this here. We have then.
hmm.
Okay,
And then we need a bunch of statements. So that
then
could very well
expression,
be a,
then
right,
expression. Okay,
right,
bunch of statement. Let's use that bunch of
right,
statement by using capital E.
right.
Okay,
And then there will be an or statement here, like after all of
okay,
this.
or statement. So
If
statement could also be if condition,
C,
then
then
expression,
expression, else,
else
and
expression.
then expression.
Okay, and there could be one more or
Or if
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 condition,
C, then E,
then E,
then else if. So
else if, right?
right.
Or
Then
else s you can say, because this entire statement can be
yeah,
true.
exactly. Right.
Okay.
So
So
this could be like else and then yeah.
yeah, so
And
this
there could be
can be
multiple
one of the this can
statements.
be yeah this can be one of the regular one of the next tree grammar production.
Yeah.
Okay, so let me just show you. Okay, I'm sharing another screen that shows you exact thing. Yes, I'm not saying that this is the wrong description that we have done. We can do this. Okay, but if you go and look into the book, okay, you will find something like this. Okay, let me just show you. Are you able to see this screen?
Yes, sir. Yes, sir.
Okay, so this is one of the thing that they have mentioned in a book. So this kind of a production, STMT,
Hmm.
okay, is on the left hand side. Okay, then arrow. This implies if expr, then STMT, else STMT. Okay,
STMT.
so all italic things are non-terminals. Okay, so
Hmm.
they have used this notion that all italic symbols, okay, with the lowercase, okay, are non-terminals, and all the bold symbols are terminals. Okay, you can use your own notation, right? So when we discussed it in an automata, we mentioned that all the small letter symbols are terminals, all the capital letter symbols are non-terminals. Okay, so we use that notion in that automata course. Okay, but that automata course, it was like, okay, adopt one particular notion, okay, and stick with that throughout. Okay, and here in this book, this kind of a notion is that italicized statements, italicized words are like non-terminals and bold words are like terminals. Okay, so these are terminals, if then else are terminals, and these italicized are the non-terminals. Make sense or not? So this is one
Yes.
kind of a statement. Okay, statement if expression then STMT else STMT. Okay, so this STMT. So then it is not expression. Now here they have not written a condition, they have written EXPR. So they have mentioned that expression is a kind of a condition. Okay, let's say if we say that if a is less than 5, okay, just for an example, this is an expression as per this definition. Okay, and STMT is the group of statement. It could be a group of statements. Then STMT else STMT. Okay, let's say if S1 and S2 are statements and E is an expression, then if E then S1 else S2 is a statement. So this whole thing is a statement. Okay, so that has arisen the definition of this. Okay, writing that this is a statement, you can say that you can define STMT, because in order to write a production, you just need a definition. Okay, so this is a definition that this starting from this to this is a definition. Okay, so once you have a complete definition, then you can write the production, right, in the form of a production. And production says that is a statement. Okay, fine, statement, I know what is a statement now. Okay, so if this can be written as EXPR, then S1 can be written as STMT, then S2, like here, S1 is a statement, S2 is a statement. This is also already mentioned. So we can write STMT here, we can write STMT here. Make sense or not?
Yes, sir.
Okay, so this kind of a structure is a recursive structure. Okay, this kind of a structure, because why do we call it a recursive structure? Because when we say that, okay, STMT is a function, just imagine this STMT is a function, and this is the body of a function. Okay, and inside the body of a function, you see that STMT is being called. This STMT is also being called. Okay, it's like we saw it in a merge sort algorithm. In a merge sort algorithm, so we were calling merge sort two times. One to get a left, sub-array, other to get a right sub-array. Okay, so this kind of a structure is called a recursive structure. So many programming language constructs have inherently recursive structure that can be defined by context-free grammars. Okay, so the usability, applicability of a context-free grammar is to define those language constructs which have inherently recursive structure, like this one. We have seen an example of a recursive structure. Okay, and this was an example. So we could also have an example of for loop, while loop, okay, other constructs which are also recursive structures. Okay, so in case of definition, in case of a definition of the context-free grammar, we have noted down that we have terminals. Okay, and terminals are the basic symbols from which strings are formed. Like if is a terminal, then is a terminal, else is a terminal here. Okay, so these are the symbols from which strings are formed. Okay, that means these are the symbols from which your you know tokens are formed, or the string of your programming language is concerned. Okay, those are formed. The word token is a synonym. Okay, is a synonym for a terminal. Okay, when we're talking about grammars for programming languages. Okay, so each of the keywords, let's say if, then, and else, is a terminal. Okay, like when we saw lex program, we took this if, we took this then, we took this else as capital if, right? Capital, then we had manifest constants corresponding to them. Okay, if you remember. So we had defined that if in a capital, then in a capital, else in a capital, as far as lex programming language was concerned, right? So these were manifest constants, and these were supposed to be returned. Okay, returned when these are encountered. Okay, so this if and this if. What is the difference in this if and this if? This if is a terminal. This if is a manifest constant that is supposed to be returned. Okay, but they are equivalent. Okay, as far as programming languages are concerned, as far as industry grammars of programming languages are concerned. But when we think of implementing some kind of a compiler, let's say Lex compiler, okay, then we can create another entity. Like here we have created capital I, capital F as another entity to define it as a manifest constant, which gets returned when small I, small f is encountered in a programming language. Okay, but they are equivalent. Okay. Okay, so then we have a non-terminal. Okay, then we saw non-terminals. Non-terminals are syntactic variables. Okay, so these are variables. That means they can take multiple forms. Okay, they can their values can change. Okay, at one point of time, expression is something else. At other point of time, expression can be something else. Okay, at one point of time, STMT can be something. Okay, another point of time, it could be with else, it could be without else. So it's a variable that denotes set of strings. Like expression denotes set of strings, stmt denotes set of strings. Okay, now in this grammar that we have just seen, stmt and exp are non-terminals. Okay, and non-terminals define set of strings that help define language. Okay, language generated by the grammar, because some non-terminals are something which are not terminals. Okay, which can generate, which can germinate multiple things. Okay, and if something which can germinate, you can take it as a seed. Okay, through which you can germinate multiple things, and those multiple things when collected together, we say that it can generate a language. Okay, that's what is meant from this statement, that the non-terminals define the set of strings. Like say we can define expression to be something, you can define stmt to be something. Okay, as expression is a set of string, it defines set of string. stmt is also defining set of string. And ultimately, when we have all the non-terminals of a programming language, and when we have definitions, when we have right hand side filled in of the production, we can say that a language is defined. So yesterday we discussed about, like, you can think of your own programming language designing. Okay, so Yash also explained his idea of a programming language. Now this is an important concept. Okay, so you also should think of writing the grammar. Okay, writing the grammar for your programming language. What are the terminals, what are the non-terminals, what are going to be productions? Okay, you have to define your programming language using context-free grammar. That's why context-free grammar is so important. Because yesterday what we saw in Sugyash's presentation, it was all like, audible? Hello, I'm audible.
Yes,
Okay, so I was disconnected. Okay, so let me just share my screen one more time. Okay, So I hope you are able to see this screen. Are you able to see the screen?
Yes, sir.
Okay. So we were talking about terminal, non-terminal, and here we have another thing called one of you mentioned that one of the non-terminal is a start symbol. So this is the start symbol discussion. Okay, then you have productions. Okay, let's say A implies alpha. Okay, B implies, let's say, beta. So these are, so alpha and beta are sentential forms. Okay, sentential form. It is a combination. It can be a combination of multiple terminals, non-terminals. Okay, capital A and capital B are the non-terminals. Okay, so this is, I mean, you can go on and write about in your own words what is a non-terminal, what is a starting symbol, and what are the productions. Okay, because we have already dealt with these things in the automata design, and you know these things, right? So in this class, I'm just revising. Okay, so that you can have a bit of idea, so that because these things are going to be used in our parsing thing. Okay, so this is an example of Ganex tree grammar. So here you have all the italics word, all the italics words are, you know, non-terminals, and everything which is not italicized, okay, is a terminal. Okay, or bold, which is a terminal. Okay, and all the operators are also considered as terminals, like id, plus, minus, multiplication, division, exponent. Okay, and this kind of parenthesis, pair. Okay, are terminal symbols. Okay, non-terminal symbols are exp, op, expr. Okay, and expr is a start symbol. Okay, one of the non-terminal is a start symbol. Okay, so here expr and op, these are the terminals. So this is one kind of example that we can think of. Okay, and so these are notational conventions. I've already mentioned about this. Let's say all italicized symbols. So notational conventions which are used in this book. Okay, all the italicized symbols are non-terminals. Okay, digits 0, 1, and 9 are all terminals. Okay, operators like plus, minus, these are all terminals. A, B, C. Okay, lowercase letters in the alphabet are terminals. Okay, and boldface, ID or if, these are terminals. Okay, and these are same, these symbols are non-terminals. Uppercase letters early in the alphabet, capital A, capital B, capital C, these are non-terminals. Capital S. Okay, like we saw this particular example here in this kind of example. Okay, though we have used it, like we have just written this statement. Okay, here I mentioned that this is italics symbol. Okay, italics lowercase letter. Okay, so this is going to be a non-terminal here, this is going to be a non-terminal here. Now we are digressing from this notion when we are formally defining it. So in the formal definition of a context free grammar, okay, they are digressing from this notion, and they are saying that, okay, in the grammars that we are going to define as a context free grammar, all the uppercase letters, okay, late in the alphabet, x, y, z, represent grammar symbols that is either non-terminal or terminal. So it is very important to understand these notational conventions, because we are going to use this. So what are terminals? So these are terminals. What are non-terminals? So these are non-terminals. Uppercase letters early in the alphabet are sure to be non-terminal. Capital A, capital B, capital C. Okay, letter S, it's a start symbol. Okay, lowercase italic names, expr or stmt, these are also non-terminals. Okay, so it is the same that we have seen just a few moments ago. Uppercase letters late in the alphabet, x, y, z, capital X, capital F, capital Y, capital Z, right? So these represents grammar symbols, which can be terminal or can be non-terminals. Okay, lowercase letters, okay, in the alphabet, chiefly, let's say u, v, late in the alphabet, let's say u, v, x, y, z, these represent set of string of terminals. Okay, so I'm just telling you, but you will get to know more about them once you make use of them. Okay, lowercase Greek letters, alpha, beta, gamma, these are sentential forms. Okay, these represent strings of grammar symbols. The grammar symbol can be terminals, can be non-terminals. When you talk about grammar symbol, it is not specific like they are terminals or they are non-terminals. They can be anything. Okay, they can be any grammar symbol. Thus a generic production could be written as A implies alpha. Okay, indicating that there is a single non-terminal on the left, and then the arrow on the left of the arrow. Okay, and that is the left hand side of a production, and a string of grammar symbols alpha. okay, which is also called sentential form, I already mentioned. And I have also been using this word sentential form in the course of automata, if you remember. Okay, so if you have multiple productions like A implies alpha 1, A implies alpha 2, and so on, A implies alpha k, all these are the productions with A on the left hand side. Okay, we can call them A productions. Okay, we can call them A production, and we can also write them using or symbol, alpha 1 or alpha 2 or alpha k. Okay, and so on. So you don't need to write, multiple statements. You can you can define such kind of A productions using one line, using or symbols. Okay, and these are all alternatives of A, alpha 1, alpha 2, and all a raised to a k are alternatives for k. So unless otherwise stated, the left hand side of production is a start symbol. Okay, so we say that if this is the expression, so capital A is a start symbol. And if we have another production, let's say E implies, okay, T plus F, so this is the start symbol. Okay, unless otherwise stated. Okay, so we'll say that this is the start symbol. So this kind of understanding that this is the start symbol, okay, this is the start symbol, the left side of the production is start symbol, is going to help you in calculating first and follow. Because in the rules of first and follow, okay, one particular rule talks about the start symbol. Okay, so start symbol doesn't mean that only there is only one start symbol which starts with capital S. Okay, there can be, let's say you have capital A, capital B, capital C. So in that case, if we are talking about this production which starts with capital A is a start symbol. If we're talking about production which starts with capital B is a start symbol. Okay, capital C is a start symbol. So in this case, when we're taking productions individually, so we'll say that start symbols are going to vary. Okay. Okay. Okay, so let's using these shorthands, okay, we could write the grammar of that particular thing, okay, as this, like 4.2. Let's just go to example 4.2. What was example 4.2? So example 4.2 was like this. Okay, I'm just slowly moving to, so this is an example 4.2. Okay, so expr can be written as capital E, because capital E here, it can be capital E. Okay, and here you can say, let's say operator is another, let's say operator is A, and then here is E. Okay, let's say if you say that A can be taken as a non-terminal for operator. Okay, so E implies parenthesized E. So this can be written this way also. Okay, E can be written as minus of E. Okay, E can be written as ID. Okay, then A can be written as plus or minus or star, because all these are OP productions. Okay, or division, or this exponent symbol. This is an exponent symbol. Okay, so this is what is meant that when we say that, okay, this can be written like, let's just carry forward to this definition. So let's say here we were talking, I was talking about, so all these were E productions. So you can also club E productions. Okay, so E productions are, let's say, so the way we clubbed A production, we could also club E production. So here it was clubbed. E implies EAE or parenthesized E or negative E or ID. So what is A? A is all about the operators. Okay, so this is what I was talking about. It's using these notational conventions or using these shorthands, you can concisely write a grammar which was written extensively in one form. You can concisely write in another form. Okay, and then let's talk about derivation. What do we mean by derivation? Derivation is like when if we have a grammar. Okay, and if we say that we are going to find out whether a particular word can be generated out of it or not. Let's say if I want to say that ID, let's say if I want to say that this is a grammar which is given, this is called expression grammar. Okay, let's say using this you can derive an expression which are addition expressions, multiplication expressions, parenthesized expressions, or negative expressions. Okay, or simple IDs. So using this, if I say that, can you derive ID star ID out of it? So if it is possible to derive this thing, okay, then we can say that it can be derivable. So you use this kind of arrow, double arrow. Okay, and you use star symbol. Okay, star symbol to say that you can derive ID plus ID star ID, okay, in 0 or more steps. Okay, in 0 or more steps. So how to prove it? So let's say how to prove it, how to go about it. If it is derivable, only then you can write it. If it is not derivable, then you can write, let's say if I ask you whether you can derive ID star from here, no, you cannot derive it. So you can write it like, okay, so you can cross this like E starting symbol E cannot derive this string. Okay, so you can cross that. Okay, I hope these two elements are clear to you. So see, if I say, can you derive negative of E? Okay, yes, you can derive negative of E. So derivation symbol is different than the implication symbol. This is an implication symbol which is used as a part of a production, and this is a derivation symbol. So this is an implication symbol, and this is a derivation symbol. Okay, so you can derive cap minus E from E in one step. If you are sure that you can derive it in one step, you do not need to write star over there. But if you think that no, there will be more steps in derivation of it, okay, then you can use star over there. Okay, star at the top. So you can write star at the top, okay, which says that 0 or more steps. So though if you write this, okay, minus E, this is also okay, fine, there's no problem in it, okay, because this star indicates that 0 or more steps, but this is one step. So one step qualifies in the range of 0 to more steps, because one is in between 0 to more, right? So we can write it, but we can also write this way, like the way it is written. E implies, derives, not implies, E derives minus E. Okay, so how do you read it? You read derives. Okay, and how do you read this? E implies minus E. E implies. Okay, so this is sorry, E implies, so this is E implies negative of E. This is E derives negative of E. Okay, so these are the things that you have to take into account when you read these statements. Okay, like E derives negativity. Okay, so this tells that we could replace, so this production tells that we could replace one instance of E, which is this instance, okay, uh, with this E, or one instance of E with this instance. Okay, this is what does it mean. So if we say that we can derive, let's say, minus of id, okay, we cannot derive in one step, we have to follow certain steps. Let's say from E you can go to, this E can derive minus E, and from this E you can say this E can be replaced with the one of the instance of E that was defined in a production. Okay, this E can be replaced with parenthesized E, and then in the next step, this E, internal E, can be replaced with ID. That was one of the form of capital E. So see, you see multiple. So E derives minus E, not derives, sorry. Yeah, derives. E derives minus E derives minus parenthesized E, and minus parenthesized E derives minus of ID in parentheses. Okay, so you see that you can state that E implies, it's not implies, sorry, E derives negative of ID in 0 or more steps. Okay, so this is what you can write. Okay, and this is the expansion of it. This is the expansion of it. Okay, so this, the process of doing this is called derivation process. Okay, I hope you're getting it. So are you getting it?
Yes, sir.
Okay, great if you're getting it. Okay, let's see example 4.4. So if I say that if I ask you whether this statement, this particular string is a sentence of a grammar or not, so how do you prove that this is a sentence of a grammar or not, or how do you disprove that this is a sentence of a grammar? So what you need to do is you just make a derivation. You need to start from a starting symbol. Okay, keep on substituting the starting symbol with the possible values of starting symbol, and then at the end you should get the string which can be derived. Okay, string which you want to derive, right? You want to derive minus id plus id. Okay, how do you go about it? So you start capital E, then you replace the capital with negative of E. Why negative of E? Because your target is negative. Okay, negative over here, then capital of E, then you need to boil down this capital of E into id plus id. How do you do that? You cannot do it immediately. First of all, you need to see that, okay, there is a parenthesis. Is there any form of capital E which involves parenthesis? Yes, there is one, which implies E implies parenthesized E, so you can replace that with. Okay, so then once you have got this also, you have got this also, then you need to get some additional expression. Okay, so is there any form of E which says additional expressions? Yes, there is one. We saw that E implies E plus E. Okay, so you can replace that E with E plus E. So here this E is replaced with E plus E. Okay, and now you want to convert this I into ID. So is there any production? Is there any possibility that we can reduce that E to ID? Yes, there is this production. So you can use this production to derive it. So id, okay, not immediately. See, you are not going to do like id plus id both at the same time, so you have to do one at a time. Okay, so you might be tempted to do it, let's say I know that e has an id. Okay, this e cannot, I can also reduce it. But if you write over here minus id plus id, then this will be a negative impact. Okay, so that will, that will cause marks to be reduced, marks to be deducted. Okay, so this thing is called leftmost derivation, because you are writing the leftmost symbol. Okay, you're taking the leftmost symbol and deriving it. Okay, then once it is done, then you move on to the right hand side. So see, when I was discussing about the last day, when I was discussing about LR parser, okay, LR parser, what do you mean by LR parser? L means left to right scanning of an input. So left to right scanning of an input means this thing. Okay, so this was what I meant from left to right scanning. So you scan this input. This is an input, right? This is an input. You scan this input from left to right. Okay, and from scanning this input, okay, you get to know about which production to imply to get to this input. You scan minus, then on the minus you got that this production I can pick, and then you scanned, parenthesis, then you got to know, okay, this is the production that you're going to pick. Then you got id. See, when you got id, you do not know that id is here. So if you do not know id is here, okay, so you can say, you can take like you, there is a mask. Okay, there is this kind of mask over the entire input. So you, here you are only able to see negative symbol, you're not able to see parenthesis id. So once minus is processed, then you replace this mask, then you shift this mask onto the right hand side, then that parenthesis appears. Now with the knowledge of parenthesis, you try to find out which production is implied for that parenthesis. Okay, and once this is done, you shift the mask onto the right hand side. Okay, I hope you're getting me what I'm talking about.
Yes.
Okay, so that way, so mask here, let me just say this is a mask. Okay, first of all, only minus is visible. Okay, just imagine that this is, so though it is transparent now, so minus, and then this, you're not sure what is inside it. Okay, so once you've seen id, then you will replace that e with id. Okay, you cannot replace this e with id here, because you do not know what this e form is, because there is a mask. Okay, and then you get plus. So plus is already there. Then you got id. So once you have got id, okay, then you go on and replace this. I hope you have understood this process. So this is called left to right scanning of input. You are scanning input from left to right. Okay, so here we are deriving by taking into account that we will not be there to derive. Okay, but computer will there to drive, computer will be there to drive, and this is how computer functions. Okay, a computer doesn't get to have the entire information in one go. Okay, it processes in a serial fashion. Okay, so that's why we have to take this thing into account. Okay.
Um, okay. Sir, I have a question.
Yeah.
When we were looking at this expression,
Mhm.
uh, right, when we find the left parenthesis,
Yeah, when we
right,
find this parenthesis, yeah,
right.
this parenthesis.
So we, from the productions, we know that there's only one production in which both the left parentheses and the right parentheses,
Mhm.
left parentheses has, right, only one
Mhm.
production.
Yeah.
So we automatically put both the brackets,
Mhm.
right?
Yeah.
And but let's just say in our program we get
Mhm.
sort of an incorrect syntax. So it is
Mhm.
minus left parenthesis id plus id, and there is no right parentheses.
Okay, so in that case, at that moment, your parsing will stop. Okay, you won't be able to, expand this thing. So it will generate an error in that case. You won't,
But
you won't reach the output. You won't reach at the end. You won't reach at the end.
okay, but isn't that, but because we are already adding uh, the right parentheses after just
See,
finding
we
left,
are adding right parentheses because we have a production of this form. That's why
right,
we have to take the entire thing. We cannot, it's not like we can take only this particular thing. Whatever
right,
on the right hand side of a production, we have to take the entire bunch and replace
entire
it
thing,
there.
right,
Okay, so we
right.
have to replace this whole thing over there.
Okay, so when, but then the mask will continue.
Yeah.
We continue processing.
Yes.
It will try to find ID,
Yeah.
it will first of all add the add operator.
Okay.
Then
Mm-hmm.
it will replace the first. Yeah, so it will replace ID, the first expression with ID.
Mm-hmm.
Then it will with the second expression with ID.
Mm-hmm.
But then it will find that okay, there is no right parentheses, maybe some other symbol or some other production.
Mm-hmm.
So then it will throw an error.
Mm-hmm. No, no. See, in
Because
this case also, let me just take this into account. So, see, once if I go on by this concept of mask. So, see, once you have recognized minus, so it can replace this with, so this kind of thing will be possible. So this kind of derivation will be applicable, right? This kind of
right,
derivation. Okay. And when you have seen that, okay, parenthesis is there, so and then this kind of derivation is possible, right? So this kind of
right,
derivation, right? So when you have seen ID, so it could mistake it and substitute it to be minus of ID, because there is something, okay, like E also implies to ID, isn't it? There was a production, E implies ID.
right,
So it could say that, okay, E implies ID. So, but once the mask is over, let's say mask is over, then it sees plus symbol. Okay. Then there will be a backtracking. It will see whether there is any production where I can replace, I can do have, I can have that plus after that ID. But here in this case, there is only left parenthesis. But in the input, you
right,
have a plus. Okay.
right,
It will backtrack. Okay. It will replace that ID with E plus E, because now the motive is to get the plus, not an
right.
ID. Okay. So some of the steps are hidden from here, but I'm letting you know that this is the process. Okay. So internally what it is going to do, because it is doing one step look ahead. Okay. Let's say minus, there's actually no step look ahead. Okay. There is zero step look ahead, because in LR parsing, in SLR parsing, I was talking about SLR parsing that day. Okay. SLR parsing is a simple parsing, simple LR parsing, where there is no symbol of look ahead. You do not see any symbol of next to, from the current input. Okay. You just have one kind of a mask thing. Okay. And you operate with that mask thing. Minus, okay, think of what production to apply. Parenthesis, think of what production to apply. Okay. ID, think of what production to apply. So this is a situation where you can mistakenly reduce this E to ID. Okay.
Right,
And then once you uncover the mask, you will find plus. Okay.
right.
Then you will find out another production of E where there is a plus. Okay. Then you will backtrack. Okay. Then you will replace that E with E plus E, though that process is not shown over here, but it is certainly the process which will be followed. Okay. And then after that, okay, mask will not be uncovered because it has already seen this ID. Okay. So then this E will be reduced to the ID, then the mask will be uncovered. So the mask will only be uncovered when the processing is complete.
Okay,
Okay.
okay. So
Okay.
it's easy.
Then now you have got ID, you have capital E here. Okay. Then your job is to convert this E into ID. There is a production where that converts E into ID. You will write that E into ID. And then you uncover the mask, and then you compare this E with this E. You declare a successful parsing.
Right.
Okay. Because
Okay,
after
so
that, there will be dollar. So after that, there will be dollar. So indication of a dollar indicates, okay, let me say, there will be a dollar at the end. So imagine that this input is in the input buffer. Okay. So this is the input buffer. Okay. So this last pointer will point to dollar. So once you get the dollar, you'll declare the successful termination of a
okay.
parsing. I hope you have understood this.
Yes, sir. So basically, we are creating a sort of a tree here. So
Yeah,
basically,
we are
creating a
creating a sort
process,
of tree. Yeah,
and
it's
then
a
we are
it's a kind of a parse tree.
right, and then we're continuously doing backtracking,
Yeah.
going back to the root, going
Mhm.
back to upper level
Yeah.
till we find something that could satisfy our requirements.
Yes.
If none satisfies the requirement, and we are up at the root, and there is no match,
Yeah.
then
Then we declare error. Yeah.
okay.
Okay. I hope you have understood everything.
Yes, sir.
Okay, great. So this is 10:29 and we don't have much time. Okay, let me just stop sharing. We'll be discussing the rest of the thing in the next class. So this kind of a derivation is the serialized way of writing a parse tree. Okay. So you can say that we can draw a parse tree in one line also. Okay. This derivation process is similar to drawing a parse tree. Okay. Linear way of writing a parse tree. Okay.
Okay.
Okay. Now I'm stopping the recording.